Hello students, we were discussing the synchronization aspects in the spread spectrum communication receiver, and most of the discussion we have done with respect to the direct sequence spread spectrum communication. In this module we will try to look into the frequency hopping spread spectrum communication system. We have discussed actually earlier in one of the modules about the FFH fast frequency hopping your MFSK system though, but in a concrete fashion how the acquisition as well as the tracking is done in general in a frequency hopping spread spectrum communication system, that was not done. So in this module first we will try to see the critical aspect of the synchronization in a frequency hopping spread spectrum system, and we would like to view few methodologies of the code acquisition and tracking in FHSS system. So synchronization, the basic principle of synchronization that we have discussed in DSSS is exactly it holds good actually same for the frequency hopping spread spectrum signal, and why it is required, why it is so critical, all those points hold good here. And we will discuss here the basically the three techniques of course acquisition for the frequency hopping spread spectrum signal. And remember that for frequency hopping spread spectrum signal, for a jammer to jam you, they need to know actually before they attack you, they need to know that at what is the synchronization process, at what point actually the synchronization is occurred in the actual receiver, and that such attacks can be very much productive also in our system design in some cases. And we need to take an example and certain example of a communication network before we enter into the different kind of the techniques, three different techniques that we have selected here for our discussion today. And today we won't be able to discuss all these three in a single module. We will start with any one of these three techniques, and other two will be consecutively discussed in the next two modules. But remember one thing, for the network, the communication network and the transceiver system that we will consider for all the discussion of all three techniques will remain same. We consider a push-to-talk network. It is a very popular network. We call it a PTN, in a way applied widely in a defense application of our country. And this push-to-talk network is the type of the network is such that you transmit the voice message, or you transmit the voice message or the voice packets over a certain period of the time, and after after one transmission, it may happen that the network is silent. I mean, there is no communication going on for a certain period of the time, and again some message is going over the network. And so the pattern is such that there is a communication and there is a wide time, actually the extended period where there is no communication, and again some voice message is going on. That's a typical architecture and nature of the PTN, push to talk networks. And in this time the clocks in the transmitter and the receiver may have so when this long gap is happening, so there is a high possibility that the clock in the transmitter and the clock in the receiver, they have got drifted apart, and they have been drifted apart, and thus causing the PN sequence codes that are getting generated in the transmitter and receiver getting misaligned to a great extent. Totally they may be out of sync also. So the logic of this PTN network, for every communication of this PTN network, is for each and every such voice packet that you are receiving, you have to perform the synchronization before each transmission or before each reception, whatever you say. So it means for respect to the every communication, you need the system, I mean transmitter and receiver needs to be synchronized, and you have to re-establish it. Actually this logic holds good for any kind of the burst communication. It is an example, a very good example of burst communication. In burst communication, a burst of the data is transmitted at one shot over a communication link, and over extended period there is no communication happens. So, data gets accumulated in a typical node over a long time interval, and it gets packetized, and then over a small packet the huge amount of the data is packed, and then it is transmitted, and then the communication is stopped. This example holds good also for sensor communication, sensor nodes and sensor communication, short range, any other different kind of the short range communications, where burst communication is a very important kind of the communication technique. And the communication that goes on in a normal commercial communication system, that's a kind of continuous mode of operation, we call that continuous communication. PTN actually falls under the type of burst communication. FHSS synchronization in PTT or PTN, push to talk kind of communication network, hence is having a very important role, because we understand that in the FHSS synchronization we are having the synchronization on the search for the synchronization will be two dimensional. One is for the frequency, another is for the code. It is equivalent to the DSSS, but here on the addition of that search of the frequency and the code, remember that there is a important phenomena called hopping of the code. So, your codes acquisition actually basically means the detection of those hopping pattern that is happening actually in the transmitted signal, and your receiver needs to get aligned with that hopping pattern. In many cases of this practical interest, such as this ground deployed push to talk communication networks, this is a safe assumption that frequency search for the code acquisition, for frequency search for the carrier acquisition actually will be ignored, because we hope that actually that's not that much important, that won't hamper actually, even if we don't considering that that is a damaging part in our kind of the code synchronization. That's a safe assumption also, because for the frequency of the carrier doesn't change a lot if it is a ground based PTT communication network, where actually today's discussion is centered. But remember, if you are moving suppose with a high velocity aircraft, then in high velocity aircraft communications, you this assumption that your frequency synchronization of carrier, if you are not done, that will not have any effect on the code synchronization or code acquisition mechanism. That assumption you cannot hold good for this high velocity aircraft. But if it is a ground based PTT communication network, where a lot of actually changes in the velocities or changes in the environment is also not, and the Doppler effect is not expected to come, then we can assume that we can actually the changes in the frequency or analysis of the frequency search can be ignored, and its effect can be ignored on the code acquisition for FHSS system. And in the synchronization method, we will start with the concept that we will send first a leader, which is transmitted prior to sending any data from the transmitter to receiver, and this leader is comprised of several passes through the hop set with a known data sequence attached with every pass. And in general, if the synchronization search fails to occur within the first pass, then we keep on searching through the consecutive passes, and additional passes can be attempted definitely. Although normally the rapid synchronization is required to maximize the data throughput. So, whether you will go ahead, actually if you completely fails in the first pass, then only you proceed for the second or third. But if the synchronization is already acquired but not occurs as per the perfection level that is expected, then whether you will go ahead to the second or third pass, that is a call, very typical call, where will you actually compromise with the synchronization, percentage of the synchronization already acquired, based on the fact that more actually you go ahead elapsed time over the synchronization process, it will bring the data throughput, it will minimize the data throughput, it will have a huge impact on the data throughput, because multiple such passes to be transmitted from the transmitter to the receiver, and that is a wastage of the bandwidth of transmission. That is why actually your data throughput is coming down. Now actually in our analysis, let us consider that the number of the hops which are associated to the synchronization sequence is denoted as capital H. Now the received signal say for the kth hopping interval of the synchronization process, which can be given by the equation 1.1. remember, this R is average power in the signal, Fk is the transmission frequency, theta k is the carrier phase, Nk is the Gaussian noise process with the variance sigma square. It can be also the power of the noise when it has a zero mean, and here we have actually assumed that the noise process is having zero mean. So basically the variance sigma square will be equal to the power of the noise, and this is related to the kth hopping interval. So the frequency, the phase and the noise all are having a subscript of k. Now after getting that received signal Rk and accumulating all those kth hopping interval, now the detection probability statistics will be defined. The probability that the test vector z crosses a predefined threshold value gamma th is going by the concept that already we have developed in the last few modules or classes, that whenever the test parameter, we always inside the correlator and the detector circuit, we always try to compare the test statistics with respect to a predefined threshold value. Whenever the test statistic crosses the threshold value, we declare that the detection is done, and all the expression of the probability of detection that we have designed, we have derived in the last modules. We have seen that it closely in presence of the additive white Gaussian noise, the detection probability closely follows the Q function, and it can be given by the QH in this case, where H is a number of the hops over which the detection probability is defined, and that will be a function of this nu and gamma dashed, where this nu is nothing but the sum of all the normalized SNRs. Rk is the power of the kth received signal, and so sigma square we understand for zero mean Gaussian noise, this is the power of the noise. So basically your nu is nothing but the total additive power over all the h hops. SNR, it is finally it is the SNR value of all the h hops, and gamma dash th is nothing but the normalized gamma value with respect to the sigma square or the noise variance. Okay. And remember, we have normalized the gamma dash with noise variance, because we try to establish that we have tried to reduce the number of the false alarm. So to reduce the false alarm rate, it is essential to normalize the gamma, I mean the SNR, with respect to the noise variance. That is the method done. We have also seen that the probability of miss is given by the complementary function, which is the total probability is 1 detection plus the miss. So 1 minus the detection probability will give you the miss, probability of miss. And if we consider that the analysis that we will be now discussing is over a Raysian fading channel. That is, a Raysian fading channel is, we will discuss a lot about the fading channels in the wireless communication class. So here actually in the Raysian fading, the distribution, the fading of the channel, actually the signal is the amplitude of the signal as well as the phase of the signal, they are getting changed, or they having lot of dispersion associated with that, and the received signal, the amplitude of the signal, they are having the fading is contributed by the Russian distribution, and the potential interfering emitters with potential interfering emitters as well as the tone jammers, they are additive to the whole communication signal model. So, there are three things that whatever the transmission power is, you are not going to expect the same power to be received in the receiver front end. The total signal will be faded by the Russian distribution of the channel, and they will have the interfering signals added to it. They will have the tone jammers added to them, and hence in the environment during the hop interval of the k, the received signal can be expressed like this, where actually this is the contribution of the interfering signals. This is the noise process as we understand, and this is the intended signal portion. We understand Fk is the frequency, Nk is the Gaussian noise process with two-sided power spectral density of eta 0 by n 0 by 2, variance is having sigma square. Remember, this sigma square is equal to n 0 into BIF, where BIF is the approximate noise bandwidth, and it is also the bandwidth of our interest. Okay. Remember this capital R, which is received power. This power is actually in a multipath environment, in a Russian fading channel environment, where you are not going to receive only the line of sight paths. You are going to receive between the transmitter and receiver, you are not going to receive a line of sight path. You are also going to receive lot of the reflected paths, which we call the multipaths in a wireless environment. This is because basically there are a lot of scatterers in the environment. The wave, the electromagnetic wave gets reflected and scattered and diffracted by these scatterers, and the scattered waves also are getting are also reaching to the receiver. So, that is why this is called the ray that is directly getting received by the receiver antenna is called the line of sight, LOS path, others are the multipaths. So, remember this capital R actually incorporates the power that is getting received by the line of sight, as well as the power that is getting received by the dominant multipaths over the environment. So, here is the direct component as well as the reflected components, and the square of the power accumulated power for over all the paths including LOS and the multipath is incorporated inside the value capital R. The factor AI here, that actually accounts the effects of the random amplitude fluctuations over the direct path and Russian channel model, and this Cj, it is actually basically the random fluctuations and the reflected components, and there are several reflected components, for example, the j number of the components that are coming here. So, the random phase associated with the direct path will be given as theta I, and with associated with the multiple paths. Each of these multiple path is having different amount of the phase associated with it. That is why theta A here actually is varying over the j in the second term. And remember that this alpha plus b, there is a consideration that we will it will have equal to 1. What is this alpha? Alpha is actually the average value of this AK over all the number of the hops, and this Cj is B is actually the summation over all the multiple paths, the addition of the Cj squares. So, alpha we can say is averaged over the each number of the hops, all the number of the hops, and this is actually a parameter which is summed over the several multipath channels. So, it is an average quantity, and this is a simple summed up quantity over the multipath channels. So, now let us consider that the number of the channels available for this FHSS hopping is denoted by capital F, and we let us assume that out of this capital F, each number of the tones containing the interfering tones. So, we have total capital F number of the channels to hop, and out of that each number of the channels or each of number of the tones, they are already they are containing the interference, and these interfering, each of those interfering signals are having the power exactly equal to the intended signal. And all the interfering signals, each of them are independent of each other also, and they are having a uniform random phase associated to them. These are basically a gross assumptions for the co-channel interference, because the interference is now coming from the adjacent channels, and they do facilitate an approximate analysis of the effects of this interfering signals. Furthermore, they are very good assumptions when the interference emanates from the multitoned jammers also, since the probability that not having any interference signal present in this whole set of the frequency channel of the capital F during a single hop can be given as 1 minus 1 by capital F of whole to the power small h. Then the probability that at least one of these tones out of capital F will have the interference is given by the pH is equal to 1 minus 1 by capital F into h. So, this is case situation that when the probability that there is not a single channels getting interfered by the interference, and hence pH is actually at least one of them is having interference. So, now let us consider that the probability that the small k number of the channels having an interfering tone will be given by the equation 1.5 by extending the equation 1.10. This can be given because you have total h number of the hops, and out of that you are saying that small k number of the interfering tones are there, and at least small k amount of them are giving the interference. And actually, if we try to extend this concept slowly and we try to find out what is the probability of false alarm now, when this is actually the probability of getting interference on small k number of the tones when capital H is the number of the total hopping intervals or hopping tones available or channels available, then we see that the probability of false alarm will be given as this equation, where this is actually function of this probability calculated earlier and multiplied with the q term of the q function, and this r k and q function will be a function of r and gamma parameter, where r k is equal to twice k L into u, and this L is the interference or jamming tone versus the signal power ratio, jamming tone to the signal power ratio, and this nu, this is equal to my capital R by Pn, where Pn is the total noise power. The total noise power means the thermal noise power plus the interference power that we are considering, and this is the SNR that we are talking about. So, we are seeing here that we are having a term Rk which is considering the interference to jamming tone given by L, the number of the tones who are considering the interference, and this nu is having this R by normalized basically a signal to noise ratio. Gamma dash we understand that this is a normalized gamma with respect to sigma square. We have normalized it because we wish to minimize the false alarm rate, and see that this total noise power Pn is given by the thermal noise power plus this B into R. Here we assume a parameter Wf which is basically 1 by Th, the bandwidth. Actually Th is the hopping duration, so basically this is the bandwidth, total bandwidth of your spreading, and QH is the generalized Q function in the equation 1.12. When the leader contains the M sequences to the synchronization duals, the overall probability function increases as reflected in a reduction in the probability of misdetection. So, this is obvious also, because if we are increasing the M sequences, number of the contains the M sequences to the synchronization duals, the overall probability synchronization will be definitely increasing, and probability that there is no synchronization is going on, that will be given by this, where this RD will be a function of this guy and gamma double dash will be a function of this. So, this is a condition that probability is not achieving the synchronization when the sync sequence is present on a single attempt. So, we call it the missed detection. Signal is present, but you could not detect it. And here comes the first technique of this FHSS course synchronization, that employs a matched filter. So, with the concept that how detection probability and missed detection probability, that is the false alarm expressions are there. Based on that, we will enter into the match filter based FHSS synchronization mechanism. We understand that H number of the hops are there that needs to be detected. So, there in the match filter architecture, we deploy H parallel match filters, and the detector is normally implemented at each of these H successive frequencies. So, the structure will look like this. So, you have H number of the match filter architecture, each of them are associated with the integration and the delay. So, this is a detector circuits that are that are associated within each and every path, and question is going on something like this. The output of these detectors will be delayed appropriately from, if it is first hop, so it will be delayed by 1, and it is a capital H hop, then it will be delayed by capital H, and addition all the output of the detectors will be added here, and then when the output of the adder, when it is compared inside the comparator with a predefined threshold called gamma TH, then depending upon the fact that which output is actually getting crossing the threshold, and based on if the sum of that is above the threshold, then the sync lock will be declared, and in that case your probability of the false lock will be given by this, and probability of the missing synchronization will be given by this, where capital H will be equal to P, the total power, and then gamma dash will be equal to gamma threshold 1. But remember here one thing, that here acquisition of that code acquisition will be really very fast, but false alarm, actually the rate at which you will get the false alarm, so that rate of the false alarm definitely will keep on increasing in this architecture. So, this architecture is very good in the case that as you are processing parallelly for the H with H matched filters, any one of them actually will give you the acquisition. So, it will have a match with the incoming signal. So, code acquisition is very fast in this architecture, but probability of getting the false lock that is also really very high. And another important part, as you are parallelly implementing each number of the match filters, hence the whole architecture is very much hardware intense. Power consumption is also very nice, power consumption will be also very high. So, we will take a very quick example to see actually how this code acquisition system will be varying with, if I take the small 5 number of the only 5 number of the interfering signals, and if we are having that there is a consider that there is no jammer, but some interfering signals are there, the 5 number of interfering signals are there, and the interfering signals from the other transmitters, they are at the same level of the signal, that means at the 0 dB, and probability of false alarm is varying with the SNR, but the threshold of this probability of false alarm for the signal design and system design, it's kept to be 10 to the power minus 4. Then you come here and see that if we are varying the number of the hops, actually the synchronization probability that is actually performing poor with respect to the SNR. You need basically the higher amount of the SNR to reach the same misdetection, to keep the same misdetection when the probability of false alarm is predefined. So that's the situation, and if I quickly look into the average time required to achieve the synchronization by the match filter process, it will be given by this equation, where the synchronization time is equal to the NC plus H multiplied by TH. H is the hopping duration, capital H is the number of the hops, and the number of the chips that you are incorporating inside that design. So this is the first method by means of which the FHSS synchronization is achieved, but we understand two fundamental points, that match filter based any acquisition technique is really very fast, because it is a parallel search going on, and it will be definitely very fast there compared to the serial search technique. But the probability of the false alarm at the same time will be keeping on increasing severely, and it is very much hardware intense. But the search time, the acquisition time is minimum compared to any other search techniques. So if you can actually really afford the high dense power consumption and high heavily intense hardware architecture, so it's always advisable to go ahead with a match filter based architecture to minimize your acquisition time in an FHSS system.